Hi, I'm Colin Walls, and I'd like to welcome you to this technical session where we're going to look at multi-core systems. Now, multi-core is a pretty big subject, so we're going to focus specifically on hypervisors and multi-core frameworks. So here is a little agenda for what we're going to cover. I'll start off by putting things in context by defining some of the concepts. We'll move on then to talk about hypervisors, then multi-core frameworks, and then we'll look at how we make the choice between these two technologies, if indeed we do need to make the choice. And then we'll wrap up. So let's look at a few concepts first of all. There's lots of terminology in the world of multi-core, lots of things that appear a little fuzzy. We'll do our best to make sure we're all on the same page. So first of all, if we consider where the embedded industry is going, well, multi-core is a big thing. Multi-core devices are incredibly complex. This diagram is not something for you to study in great detail, but it gives you a feel for the scale of what this technology is like. It gives you a feel for the consolidation of technology onto a single chip. And this brings with it lots of interesting challenges. The hardware consolidation is one aspect of it, simply the building of system on chips. And this is bringing together multiple systems and subsystems onto a single piece of silicon. The benefits of doing it, the positive side of it, is we reduce costs. We cut down the bill of materials and we tend to save power as well. So many modern devices would not be possible without system on chip technology. At the same time, we can increase performance and we can increase the capacity of systems way beyond what we could do before. These are the things that multi-core brings us as benefits. The downside, there are concerns. The concerns are mainly around complexity. Complexity of the system design, complexity of the development process, debugging, isolation between different components, particularly in the context of where you have systems where safety and or security are important. So many things to think about here. There's a trend towards heterogeneous multiprocessing in embedded system-on-chip devices. The heterogeneity occurs in hardware, in that we have multiple cores of different types. We may have application devices, real-time cores. There may be digital signal processors, FPGA soft cores, and a variety of other possible devices in there. So a big mixture of different hardware. If we move on from there, we have heterogeneity in the software. The software can consist of different operating systems, different other software components. There may be no operating system. We might be running software on bare metal. We may be using real-time operating systems. We may be using multiple real-time operating systems. This heterogeneity is another facet of the complexity of such a system. And to build a system successfully, we need a asymmetric multiprocessing paradigm. This basically means that we have to provide facilities for communication and sharing of workload between the different software and hardware components. It also means we have to control how the system starts up and manage it thereafter. Those are the two big challenging areas. Let's first of all ponder multi-core hardware. The processor configuration could be almost any combination of CPUs or specialist processors like GPUs and DSPs. They could be all the same, they could be all different. We'll consider the possibilities. A homogeneous multi-core is where we have lots of processors and they're all absolutely identical. This is somewhat typical of the computer sat in front of you. Most desktop computers are homogeneous multi-core devices. The next possibility is heterogeneous multi-core, where the cores are all different. They may be completely different, they might be slightly different. It could be a complete hodgepodge of different types of core. Most systems, however, are some amount of hybrid. There may be multiple cores that are the same, but some are different. There may be high and low power options, or maybe there are regular CPUs and some specialist cores of some kind. So the possibilities are quite complex. If the hardware architecture is complex, the software architecture is potentially even more so. There are more options, and we'll consider these fairly quickly. The symmetric multiprocessing. Symmetric multiprocessing is when we run a single operating system across multiple cores, and this enables you to create a more powerful execution environment. We have asymmetric multiprocessing, and this is when we would run different software on each core, and it may be very different, it may be somewhat different. It could be different operating systems, and the cores can all be different hardware. Incidentally, there may be islands of cores which are SMP computing domains. So an SMP system can exist within an AMP system. We can create systems with unsupervised multiprocessing, where there's no real separation between the cores. Each core, each operating system runs by itself. They coexist and they function in a cooperative fashion. Or we can do asymmetric multiprocessing with separation using facilities on an SoC. The SoC may have capabilities for separating different components within the device. Or we can build a supervised multiprocessing model with separation and virtualization capabilities. This means that we're going to use the OS environment with a hypervisor, and the hypervisor will enforce the separation between virtual machines, giving us a very high degree of separation. And this is particularly important in certain safety critical applications. So we have a wide range of possibilities here. So start with symmetric multiprocessing. The point here is we are using multiple cores to provide more computing power. So we run an operating system across multiple cores. In my diagram here, I'm showing 4 cores on the left-hand side running an instance of the Nucleus operating system in its SMP form. And then the application software runs on top of that. The scheduler within the operating system will maintain distribution of work across the cores. You have control over it as well if you want, but it can be done automatically. This capability is available on a variety of RTOS products on the market, and also Linux has an SMP option. If we look at asymmetric multiprocessing, it's a little more complex. If we start on the left-hand side, well, I've introduced here 2 different SMP configurations. So on the left-hand 2 cores, we have running Linux in its SMP form. The next 2 cores in are running Nucleus SMP. And on the right, we have some other cores. One of them is running Nucleus by itself. Another one is running no operating system at all. It's bare metal. So this is a much more complex system, lots of different kinds of software running. And we have to consider how we would manage this system, how we communicate between the components, and how we distribute work between the hardware and the software. So we move on to how we address those particular issues. And one way we can do it is by means of a hypervisor. Now, hypervisors are something which many people will have heard about because they're used in lots of contexts. We are focusing very much on the multi-core context. So a hypervisor is a fairly complex, very versatile software component. Broadly speaking, it enables the supervision of multiple operating systems. It will control their access to CPU and peripherals. It provides communication between the operating systems and provides isolation between them. It will work in a multi-core context, takes care of things like boot sequence, and manages the sharing of peripherals. The separation means that if a particular subsystem crashes, it won't bring down the rest of the system. They're suitably insulated. A key thing is to consider we're working on embedded systems, and embedded systems really require a hypervisor focused on those needs. Now, there are pros and cons of hypervisors. Pros, first of all, good positive start. They're incredibly flexible. They enable very efficient sharing of resources, which can be dynamically adjusted, relatively low latency, and very high bandwidth communication between the virtual machines. It provides extremely strong separation between the cores and enables us to virtualize devices for sharing. There is the possibility to assign ownership of peripherals to particular cores as well, rather than sharing them. The downsides of hypervisors is they tend to be quite large pieces of software, quite a big code footprint. So if memory is an issue, hypervisors might be a problem. Similarly, they require a significant amount of CPU time. There is a significant execution time overhead. A key limitation or feature, depending how you look at it, is they will only work on a homogeneous multi-core device. So a device where all the cores are identical. It also requires hardware virtualization enablement in the processor to perform that operation. So, and they have limitations in those areas, and they're also quite complex overall. So hypervisors, whilst they give a lot of power, do cost something in terms of resources one way or another, and limitations on your design if we look at the homogeneous multi-core requirement. There are other possibilities that might be more attractive. The obvious alternative to a hypervisor is a multi-core framework. This is terminology which is not that familiar. It's technology which has really only emerged in the last few years as multi-core has become more common, bearing in mind that hypervisors are used in single-core environments as well. A multi-core framework is a means of enabling an asymmetric multiprocessing software architecture. It is designed very, very specifically to support the multi-core application, and it provides two key pieces of functionality: communication between the processors or between the operating systems, depending how you look at it, and it provides lifecycle management, which means things like boot order can be controlled. It provides these facilities with a very low overhead, and it can be run on much more basic systems than a hypervisor. A hypervisor needs an operating system on every core. A multi-core framework does not necessarily require an operating system. We can run it on bare metal if we want to. So we have a great deal more flexibility with a multi-core framework. So pros and cons again. Pros. Lots of advantages of multi-core frameworks. They're very good at implementing a system where the timing requirements of different processors is very different. We can migrate legacy software more readily because we can have lots of different processor architectures and different operating systems. And it enables us much more flexibility in our design pattern because we're moving away from homogeneous multi-core. Embedded engineers tend to be very picky about software where they feel they're getting functionality they do not need. Extra overheads are a problem. The beauty of a multi-core framework is it provides just the required functionality. So that's the interprocessor communication and lifecycle management. The memory footprint is pretty modest, and the execution time overhead is not bad at all. The key thing is that it can work on a heterogeneous multi-core device. We do not require any similarity between the cores. And there is no requirement for an underlying OS. You can use bare metal if that suits you. It's relatively unlikely that a sophisticated application will need to run components on bare metal, but if you need that last bit of performance, it's an option. The downsides of multi-core frameworks. Well, there is no built-in isolation of resources. It assumes cooperative operation. There are possibilities for overcoming that problem. If you have suitable components in hardware, a system controller, for example, in some devices will enable the multi-core framework to achieve greater separation. Hardware protection unit of some kind is what we're looking for there. Let's consider some examples of multi-core frameworks. The best starting point, for example, is OpenAMP. Now, OpenAMP is an open standard for asymmetric multiprocessing. It's a framework which does what I just said we need. It provides communication between cores, and it provides lifecycle management. So this is an open standard. You can download software and example software from the website, and you can find every last detail that you want there. So that's our good starting point on the left-hand side of the screen here. On the right-hand side, here are a couple of examples of proprietary implementations of a multi-core framework. The Mental Embedded Multicore Framework is a proprietary implementation of OpenAMP, and it does everything the OpenAMP specification says it should do, with the additional functionality of support for Linux as a remote, large buffers, zero copy communication, and proxy support for Ethernet. So some additional functionality there. The Mental Embedded Multicore Framework CERT is designed for systems with certification requirements. So systems typically with mixed safety criticality. The communication provided by this framework is between the safe and the non-safe domains. And it has various extended facilities, including ability to do static and dynamic code analysis that's necessary for certification. We'll talk some more about this shortly. So how do we make the choice between a hypervisor and a multi-core framework? You probably need one or the other, or maybe you need both. That's an interesting possibility. So making the choice depends on many design factors. The hypervisor means you have to have a CPU on every OS, and all the CPUs must be identical. Multi-core framework can work without a CPU, without an OS, and lots of CPU architectures can be supported. The hypervisor provides a very robust isolation, but a multi-core framework can use hardware isolation if it's available. And the bottom line is there are many possible configurations. I'm going to go through a few examples. This is not exhaustive by any means. Let's start off with something simple. Here is an AMP system. We have 4 cores. We don't know their architecture, but let's assume they're the same. We're running 4 operating systems on them, which may or may not be the same. And each of these incorporates a multi-core framework. That enables us to build a system which will do the job. It's a very simple system. We could make it slightly more complex. We can add another couple of cores, maybe a different architecture. We're running OS 5, whatever that is. Here's another operating system. And we're running some code on bare metal on the right-hand core there. We could reconfigure the system slightly. And in this case, I'm now running an SMP operating system across the 3 cores on the left and a standalone operating system on the other core there. And with the right-hand side is much the same as it was. We could go even further. We could run an SMP operating system across all the cores on the left-hand side and another SMP operating system across the cores on the right-hand side. And we're still using the multi-core framework to communicate and control the system. We can introduce the use of a hypervisor. Now, in this case, I'm still running different operating systems. I've got one operating system, OS 1, running on one core. I'm running OS 2, which is a SMP operating system across another couple of cores. And I've got OS 3 on the right-hand side there, running on the 4th core. And we have the hypervisor controlling these systems, controlling their boot order and so forth, and providing communication between them. We can add to the system a little bit more. So here I've left the hypervisor in place, but I've pulled off OS 3 and made it standalone. We've now got OS 4 and the bare metal there again. And we were using the multi-core framework and the hypervisor. So the hypervisor is providing very detailed control of the OS 1 and OS 2 components. And then the multi-core framework enables us to communicate and control across the entire system. And the last step is if we put in some hardware separation, if we put in a barrier within the hardware between the cores on the right and the cores on the left, we then have an opportunity, which is to certify parts of the system. So if your application has safety certification requirements, you would normally have to subject all the hardware and all the software to the certification process. Certification is expensive and time-consuming. So if we can segment our system so that the part which is associated with safety activity is completely separated from the rest of the system, then we can do two things. Firstly, we have less certification to do because only the bit on the right-hand side of this diagram needs certification. So that reduces costs and time. And also, on the left-hand side, the software can include legacy components and a choice of operating systems as we see fit without having to think about the certification requirements of those. So it gives us more efficiency with the development on the left-hand side and reducing the cost of certification on the right-hand side. Let's consider what this really means, because with mixed safety criticality, we mean our system has different levels of criticality on either side of that barrier. So from the hardware design point of view, we need to think of temporal and spatial isolation. We need hardware semaphores for sharing of resources. And of course, the silicon would need to be certified for the components which are relevant. From the software design, it's a very good design using AMP for mixed criticality, because it means we can mix the safe and the non-safe all on the same chip. We can reuse software, and we can use the hypervisor where it's appropriate. And the most important thing is lowering the cost of the certification. Let's look at some real solutions to this kind of technology. So, our multi-core solutions. Mentor offers three particular components. There is the Mentor embedded hypervisor. This is a hypervisor, has all the functionality that I've talked about earlier, and is specifically designed for embedded applications. So it's not designed for single processor usage like some hypervisors are. It could be used in that mode, but it's designed for multi-core. We have the Mentor embedded multi-core framework. This, again, has the characteristics I talked about. It provides the functionality that you need on homogeneous, or more likely, heterogeneous multi-core processors. And then we have multi-core framework cert. This is a variation on the Mentor embedded multi-core framework, which has certification characteristics. Basically, it's been designed with the need for certification in mind, and there are a number of resources available to make that process simpler. So the Mentor embedded hypervisor, it's multi-core capable. You can have multiple OSs, of course, and it has full security enablement. The footprint and the performance of it are pretty good for a hypervisor. Hypervisors tend to be large, complex pieces of software, but the Mentor embedded hypervisor is relatively small footprint and has good performance. It's a comprehensive solution because we do not just provide the hypervisor, we provide all the necessary tools to implement it. The Mentor embedded multi-core framework, again, it is enables you to build a system by itself, an unsupervised AMP system. It provides the functionality you need to control such a system, and essentially the two lots of functionality are lifecycle management and interprocessor communication. Combined with the use of a hypervisor, you can build a supervised AMP system if you need something more complex. The multi-core framework safety certifiable solution is very similar to the Mentor embedded multi-core framework, but is specifically oriented towards safety critical systems. There is comprehensive documentation and components available to enable certification in a number of industries, together with the necessary tools. The key functionality we are looking at is building systems with mixed safety criticality, thus reducing the cost of certification by only certifying the parts that are necessary. Heading towards wrapping up now with a few conclusions. First of all, the choice between a hypervisor and framework is something that needs to be considered, but it's a very much a non-trivial decision. There are a wide range of factors. As always with embedded development, it's essential to use products that are made for embedded. Otherwise, you'll probably find there are overheads there you don't need. And the Mentor Embedded Hypervisor and the Multicore framework both fit the bill here well, and they work seamlessly, of course, with our Nucleus real-time operating system and Mentor Embedded Linux. But remembering that the Multicore framework is OpenAMP compliant. So we have a comprehensive range of products, including 2 variants of Linux, a source-based, very flexible one, and a binary-based Linux implementation. There's Nucleus real-time operating system. There's Nucleus Safety Cert RTOS. This is aimed at certified applications. There's Mentor Embedded Hypervisor and the 2 frameworks I mentioned. There's also a Mentor Embedded IoT framework if you're building that kind of application. This is backed up with tools, the Sorcery Codebench development tools, bring all these together to enable you to complete an application. One of the challenges with multi-core applications is finding out what they're actually doing. So the last tool in the chain there, which is worthy of a presentation all by itself actually, is the Sorcery Analyzer. This enables you to get a very detailed view of what's going on across the entire multi-core system. That completes what I have to say to you today. Here are my contact details and details of my blog. And I'd be happy to hear from anybody after the session if you have any questions or comments. So thank you for your time.